This is example 4.2.3. It says a ball is launched horizontally off a cliff that is 50 meters high at a velocity of 35 meters per second. Determine where the rock lands. So we're going to go ahead and just show a picture. We're going to have a ball that's being launched off of a cliff. We know that it is launched at a horizontal velocity of 35 meters per second. We also know that the cliff is 50 meters tall. We want to know where it lands. So our given information, we're going to go ahead and we're going to find delta dx, or the displacement. We know that this is a two-dimensional problem. Okay, so since we know it's a two-dimensional problem, it's going to have x's and y's. I know that in the x direction, I only use v equals delta d over t. That's the only equation that I can use in x. In the y direction, I know that I'm going to use if that, depending on what I'm trying to find. So let's look at our given information in the x direction to begin with. Okay, in the x direction, I'm given that the velocity is 35 meters per second, and that's all I have. In the y direction, the only thing that it tells me is that the ball is launched off a cliff that is 50 meters high. Well, 50 meters high means that the ball has to have a displacement of -50. And this is somewhat confusing for some people, so let's look at our drawing. The ball is actually going to go down 50 meters. So it's going to be -50 from its initial position. So that's where we get this negative term from. We also know that the acceleration is -9.8 meters per second squared. It's under the influence of gravity. And then we also know that the initial velocity is 0. And the reason why we know that, it says the ball is launched horizontally. Well, horizontally means that there's no vertical component to begin with. Now remember, the key to these problems is to solve for time. So if you look, I don't have enough information to solve for time in the x, but I do have enough information to solve for it in the y. So what I'm going to do is I'm going to do if that. And I'm going to say, okay, I have initial velocity, I have distance, and I have acceleration, and I'm trying to solve for time. That means I pick the equation that does not have final velocity in it, and we've said over and over again that that is delta d equals vit plus 1/2 at squared. So now we're going to go ahead and plug our numbers in. Remember, actually we're going to rearrange first. Because this initial velocity term is 0, that term cancels out. So when we rearrange this equation, it's much simpler. We can say, okay, multiply both sides by 2 over a, and you get 2 delta d over a equals t. Remember, this is squared, so I'm going to take the square root of both sides, canceling that out, and you get that t is equal to 2 delta d over a, all of it under the square root sign. So once you have this right here, you can now solve for the time. So you say 2 times -50 divided by -9.8, take the square root. So 2 times -50 is -100. -100 divided by -9.8, and you get 10.2. Take the square root of that value, and you get 3.2 seconds. Now, if you were to make a mistake and not originally say that this 50 is negative, you would have positive here, which means you'd have a negative value in the square root. That would give you an imaginary number, something that you can't use. Your calculator will say that's undefined. So if you ever get that, just realize that you made a mistake somewhere with a negative sign, and you need to go back and find it and correct it. So now that the time is 3.2 seconds, remember the whole purpose of solving for time is time can cross over into the x variables. So now I can apply it, and I can say v equals delta d over t, or delta d equals vt, rearranged, which is equal to 35 times 3.2, which if we go to our calculator, 35 times 3.2 gives us a value of 112 meters.